Hey, what's up everyone? This is Physics for Engineering, and today we talk about the Newton's first law and mechanical equilibrium. Isaac Newton, an English mathematician and physicist, has compiled the three laws of motion in his Mathematical Principles of Natural Philosophy, first published in 1687. Three physical laws that together laid the foundation for the classical mechanics. They describe the relationship between a body and the forces acting upon it, and its motion in response to those forces. And today we talk about the Newton's first law that can be stated mathematically as F equal to 0. The Newton's first law states that if the net force is 0, then the velocity of the object is constant. Here the net force F is the vector sum of all forces acting on the object. Let us take some example. We have a stationary car, its velocity is 0. Newton says in this case, since the velocity of the car is 0, then result force acting on the car is also 0. Let us check what does it mean for the car. We define first the forces acting on the car. This is the gravity force, and these are the reaction forces acting on the tire wheels. Newton says that since the velocity of the car is 0, then the result of all forces acting on the car is 0. We define the coordinate system and write the projection of all the forces on y-axis. This gives us the following equation. So that the reaction forces acting on the tire wheel are equal to the gravity force of the car. So this is what we have from the Newton's first law in this case. Okay, let us now take another example. Imagine we have a car which is moving with the constant velocity v. In this case, the Newton says that the result forces acting on this car are equal to 0. Let us now check what does it mean for this car. Let us define the forces acting on the car. We have a driving force from the engine Fd, and before the Newton there was an opinion that the constant velocity of the object is the product of the constant force acting on this object. Newton says this is not the case. In our case, we have another forces acting on the vehicle. These are the rolling resistance forces and air resistance force. We also add here the forces acting in the vertical direction. These are the gravity force and the reaction forces acting on the tire wheels. And Newton says, since the vehicle moves with the constant velocity, then the result force acting on the vehicle is equal to 0. This is the driving force, two forces of the rolling resistance, the air resistance, the gravity force, and two reaction force on the tire wheels. We define now the coordinate system and write the projection of all forces on y direction, and we obtain the equation from the first example. Then we write the projection of all forces on x direction, and we obtain the following equation, that our driving force is equal to two rolling resistance forces acting on the tire wheel plus the air resistance force. So these two results follow from the simple definition of the Newton's first law. If we have a vehicle moving with the constant velocity, then our gravity force equal to the reaction forces acting on the tire wheel, and our driving force is equal to the rolling resistance acting on the tire wheels plus the air resistance acting on the cabin of the car. But in some cases, the Newton's first law is not sufficient to describe the mechanical system in the equilibrium. Let us take one more example. We have a crane, and our task is to determine the following: the weight of the balance M capital required to lift the weight M small, and the second task is to calculate the load on the chassis. Okay, let us define the forces acting on the crane. So this is the gravity force of the weight, this is the gravity force of the crane itself, and this is the gravity force of the balance. We call these forces correspondingly F1, F2 and F3. We have also the reaction force on the chassis of the crane from the ground, N1 and N2. We will consider that reaction on the left chassis is 0. In such a condition, we calculate the minimum mass of the balance required to lift the weight. According to the Newton's first law, all the forces acting on the crane are 0. We define now the coordinate system and write the projection of all these forces on y-axis. As a result, we get the following equation: the relation between the force on the chassis and between the mass of the balance, of the crane and of the weight. MC is the mass of the crane. But we have two variables in this equation, because the mass of the balance is not known. Therefore, the Newton's first law is not enough to describe this system. In order to solve this problem, we need to consider the following conditions for the mechanical equilibrium. That the body is in mechanical equilibrium if the net force on that body is zero. This comes from the Newton's first law. And the second condition of mechanical equilibrium, that the net torque acting on this body is also zero. The body in mechanical equilibrium has a constant linear velocity and constant angular velocity. These rules are extremely important in solving various problems in physics and mechanical engineering. Let us now come back to our problem with the crane. We have used already first condition for the mechanical equilibrium, F equal to 0. Let us now use the second condition, M equal to 0. The result torque acting on the crane is equal to 0. We move our coordinate system to the front chassis and write all the torques acting on the crane around this point. We need of course the lever arms of each torque acting on the crane. Suppose this is given. With consideration that the torques acting in clockwise direction are positive and in counterclockwise direction are negative, we come to the following equations. And the result is the formula for calculating the mass of the balance, M capital. We see that the mass of the balance is proportional to the weight and inversely proportional to the distance A between the chassis, between the front chassis and the balance. The mass of the crane also reduces the weight of the counterbalance, because then the crane itself can play the role of the balance. So finally, using the condition for the mechanical equilibrium that F equal to 0 and the M equal to 0, we were able to solve our problem. The conditions of the mechanical equilibrium are applicable for any system which is moving with the constant velocity and spinning with the constant angular velocity. In this case, the net force on the body is 0 and net torque acting on the body is also 0. The conditions of mechanical equilibrium are fundamental by solving various problems in classical mechanics, statics, physics, and have a direct practical use in mechanical engineering. We will solve further many problems, sometimes complex problems, with consideration of the mechanical equilibrium. So please subscribe and see you next time.